This is the future of home device control. This project has been long in the making, and after a year of testing, tweaking, retesting and retweaking, it has come to a point where I would consider it to be a successful prototype. The purpose of this project is to create a device that can be used to reduce the amount of e-waste created by a population by allowing people to upgrade their existing dumb appliances instead of adding to the already massive e-waste problem that we have in our hands. The way I went about accomplishing this was to create a box that features two power outlets that can pass through power from a wall using two switches that are controllable via a microcomputer called an Arduino that's located inside. These two outlets are individually controllable, and this allows the user to control two devices individually by using a phone app that interfaces with the Arduino using Bluetooth Low Energy, or BLE for short. The app allows the user to fine-tune the environmental trigger conditions that cause the outlets to restrict and allow the flow of power. The interface of the app shows the user readouts of the temperature and humidity of the surrounding environment, which allows the user to make a better decision regarding what to set the thresholds for the humidity and temperature screens. There is a master power switch that can be toggled on and off to allow the device to act as a regular wireless power switch, so that in the case that there is already a system in place for managing the climate, the project can still be used for a different purpose. As alluded to above, the app has three different tabs that consist of the main information screen, which has the master controls, readouts of the current status of the outputs shown by the virtual LEDs above the master switch, and the current readings for the temperature and humidity in the environment. The second tab allows for the user to individually set the outputs to be triggered by a temperature threshold, and lets the user define this threshold using the two sliders at the bottom. The third tab is the same as the temperature section, but instead allowing control of the humidity threshold and whether the outputs are affected by this threshold. There were three main options I had regarding the communication protocol used for interfacing the Arduino and the app, with these being Wi-Fi, Bluetooth and BLE. After doing more research into Bluetooth, I decided it wouldn't be the best option for the project, since the only Bluetooth modules available for Arduino used an ancient version of Bluetooth that was prone to disconnects and had major problems regarding interference with 2.4 GHz Wi-Fi signals. For testing the other protocols, I set up an Arduino and an ESP32, with the Arduino running the HM10 BLE module and the ESP32 using its integrated Wi-Fi hardware. This test revealed that while using a stable network, Wi-Fi significantly outperformed BLE regarding speed, connection integrity, and delay. But as the main network at school is extremely unreliable, I found that I wasn't able to get the ESP32 to connect when attempting to redo the test a second time using the school's network. This meant that my only choice for wireless communication was BLE, due to the context of having to create and test the project using solely the school network. This was an issue because it severely restricted my options for app creation, with documentation on interfacing an Arduino with BLE being scarce at the time. When looking into interfacing a smartphone with an Arduino, there were many options that were available at the time, but only two that really appealed to me. The initial plan was to create an app using EvoThings Studio, which is a platform that allows creation of apps using Java and HTML. This initially seemed like a good base to build the app upon due to having previous experience in HTML and wanting to learn about Java. After looking for documentation on how to integrate BLE into an app using ETS, I found that there wasn't any documentation on how to do it. This meant that I had to move on to my second option, which was Blink. Blink ended up being a much more plug-and-play approach, which I already knew would happen because of my previous experience using it. Unlike ETS, Blink had support for BLE, even if it wasn't as well implemented as the other connection options were. The support for BLE was what ended up deciding for me. There were other aspects of using Blink that ended up working to my advantage, such as the nicer interface and the ease of setup, meaning I could allocate more time to creating the code for the Arduino. I wanted to make the code as modular as possible, so that if I decided to add or remove any part of it, the rest of the code would be affected as minimally as possible. The libraries used consist of the generic Adafruit sensor library for the BME280 humidity and temperature sensor, the EEPROM library to allow the use of the Arduino's built-in storage, the Adafruit RGB LCD library for the display, the Blink library to allow Blink to recognize and respond to data inputs and outputs, and the simple BLE library to allow Blink to communicate over Bluetooth Low Energy. The setup of the code is fairly straightforward, with there being two relays, an LCD, and the BME280 sensor to configure. There is also a timer set up using the simple timer library that I failed to mention above. This timer is going to be the main sync event for reading and writing data to and from the Blink app. This timer is also responsible for keeping the EEPROM up to date and running other background tasks, such as ensuring that the sliders in the app aren't able to overlap each other. This last section of the setup code is the error checking that I've implemented to troubleshoot the BME 280. This section of code will halt the code and display a message on the LCD to alert the user that there is an issue. Going on to the main loop is where we find the bulk of the functions that make a majority of the code. In these functions we find the code that reads the EEPROM on startup along with the control logic that interprets the data read from the app and decides what to do with the power outputs depending on the variables read. There were many problems I faced along the way regarding the creation of this project, with the biggest one being the faulty sensor that made me replace half of the hardware and recode the whole sketch again. The issue was that after a few hours of running perfectly, the sensor would start reporting gibberish which would break the whole system. I originally thought it was a power issue with interference coming from the power supply, but I ruled that out after trying to run it with the relays disconnected. It turned out that the sensor was damaged in a way that it still worked until the smallest voltage dip or spike happened, which would throw it off. It must be noted that issues like these come with doing an electronics-based project, which can make the debugging process even harder than running code in an IDE. Overall, this project has been an interesting voyage into the intricacies of Arduino code, which is on a level beyond my previous year's project. If I could change anything about how this project turned out, I would have delayed it a year, because between starting the project and now there's significantly more information released on BLE and Arduino interaction, and in my free time I figured out how to interface these manually. This would have changed the whole course of my project and likely made it more flexible, opening possibilities such as Google Home integration and other IoT integrations. Because of this, I still consider this a work in progress and will continue to iterate on the design in my free time after this assessment is complete.